Okay guys, let's talk about the CBSE pattern question exercises on mathematical induction. The first question for 1 mark says that Pn represents the statement nq plus n is divisible by 3. Is the statement P3 true? Is the statement P4 true? If Pn is nq plus n is divisible by 3, I need to talk about the truth value of P3 statement and the truth value of P4 statement. P3 says that 3q plus 3 is divisible by 3. That is, what is 3 cube? 27, 27 plus 3, 30. 30 is divisible by 3, which is clearly true. 3 into 10 is 30, so 30 is divisible by 3. If I talk about the truth value of P4 statement, which says that n cube plus n, so 4 cube plus 4 is divisible by 3. 4 cube is 4 into 4, 16, 16 into 4, 64, 64 plus 4 is 68. So you have, that is 68 is divisible by 3. When you add 8 and 6, you don't get any number which is divisible by 3. Do you get? 8 plus 6 is 14 and 14 is not divisible by 3. So by divisibility test of 3, I know 68 is not divisible by 3. So which is false. So we are getting that yes, P3 is true, but the statement P4 is not true, it is false. So out of the two statements, P3 is true, P4 is false. Moving to the next, we have Pn is representing this given statement. Prove that P3 and P4 are true, but P5 is not true. So already we know what we are supposed to show. P3 and P4 we have to show, verify, justify that that is true, and P5 is not true. Pn is n into n plus 1, n plus 2 is divisible by 12. If I talk about P3, it is 3 into 3 plus 1 into 3 plus 2 is divisible by 12. That is what? 3 plus 1 is 4, 4 into 3 is 12, 3 plus 2 is 5, 12 into 5 is 60. So you have 60 is divisible by 12. Clearly it is true. So we have justified that P3 is true. If I talk about P4, P4 will be 4 into 4 plus 1 into 4 plus 2. This is divisible by 12. This is my statement P4. That is what? 4 plus 1 is 5, 4 plus 2 is 6, 6 into 5 is 30, 30 into 4 is 120. So we actually have 120 is divisible by 12, which is again true. 12 into 10 is 120. But if I talk about P5, what do you get? 5 into 5 plus 1 into 5 plus 2 is divisible by 12. That is, this is going to give you 210 is divisible by 12. Clearly 210 is not divisible by 12. So this is false. So based upon statements, you can get questions like these in your paper, okay? Next question we have, Pn is representing the statement 7 divides 2 to the power 3n minus 1. What is Pn plus 1? Clearly if you have a statement in terms of n and that is represented by Pn, what would be the statement Pn plus 1? It would be the same statement with n replaced by n plus 1. So Pn plus 1 would be nothing but 7 divides 2 to the power 3 bracket n plus 1 in place of n minus 1. If you want, you can resolve this. This means 7 divides 2 to the power 3n into 2 to the power 3 minus 1, that is 7 divides 2 to the power 3n into 8 minus 1. That is your statement Pn plus 1. Next we have what? If Pn is this particular statement, prove that if Pr is true, then Pr plus 1 is also true. So let us assume Pr is true. Let Pr is true. R is natural number. R is belonging in the set of natural numbers. We know this Pn, where n is in the set of natural numbers or positive integers, which is natural numbers itself. Let Pr be true. If Pr is true, that means this statement is true. This implies R square is greater than 100. This is true. This means R square is greater than 100. If Pr is true, that means this statement is true, that means R square is greater than 100. If R square is greater than 100, I have to show, if Pr is given to be true, I have to show Pr plus 1 is true. That means I have to show that Pn is n square is greater than 100. So Pr plus 1 will be R plus 1 square is greater than 100. R plus 1 whole square is greater than 100. I have to show that this holds. Whenever Pr is true, then I have to show Pr plus 1 is also true. Now Pr is given to be true. We have R square is greater than 100. This is already true. Now I am saying adding 2r plus 1 on both sides. R is a natural number, please remember, okay. So 2r plus 1, 2 into a natural number plus 1 is the quantity greater than 1. This is a natural number greater than 1. So if I do that, I get R square plus 2r plus 1 is greater than 100 plus 2r plus 1. As I just said, 2r plus 1 is a natural number greater than 1 because R is a natural number. So 100 plus 2r plus 1 is a natural number strictly greater than 100. If this 2r plus 1 is greater than 1, then 100 plus 2r plus 1 is greater than, obviously greater than 100. This is greater than 100. And what is R square plus 2r plus 1? It is R plus 1 whole square. So if I am assuming R square is greater than 100, I am getting R plus 1 whole square is also greater than 100. That means if Pr is true, then I am getting Pr plus 1 is also true. Therefore, Pr plus 1 is true. Clear? Moving to the next question. Prove that 2 to the power n is greater than n for all positive integers n. Either you say positive integers or you say set of naturals, it's exactly the same. Whenever we have to prove this for all positive integers n in the set of natural numbers, we use the principle of mathematical induction. What does it say? Well, let Pn represent the statement 2 to the power n is greater than n. You start with n equals 1. P1 is 2 to the power 1 is greater than 1, that is 2 is greater than 1, which is clearly true. Obviously 2 is greater than 1. If P1 is true or Pn is true for n equals 1, next step is let Pn be true for n equals k for some positive integer k, which implies let Pk be true. Pk be true means if Pn is 2n is greater than n, 2n is greater than n, Pk is true means 2 to the power k is greater than k. This is holding, that means this statement is true. If induction hypothesis step has been done, that means I have assumed Pk is true. With this assumption holding, I need to show Pk plus 1 is true. That means I have to show what? Pk plus 1 is true means I have to show 2 to the power k plus 1 is greater than k plus 1. I have to show this. And I am already given Pk is true. So as Pk is true, this is given to me. This implies 2 to the power k is greater than k, if you multiply both sides by 2, multiplying 2 both sides, what do you get? You get 2 into 2 to the power k is greater than 2k. 2 is a positive number. When you multiply on both sides of the inequality, inequality doesn't change. This means 2 to the power k plus 1, because this is 1, is greater than k plus k. But k is a natural number. K is always greater than or equal to 1. So k plus k is always greater than k plus 1. Is it okay? See, for 1 already the statement is true. If I am assuming that it is true for some k, k is obviously different from 1, greater than 1. If k is definitely greater than 1, because for 1 it is already true. If I am assuming for pk, if I am assuming for k, pn is true, then this k is definitely greater than 1. If k is greater than 1, k plus k is greater than k plus 1. And this implies 2 to the power k plus 1 is greater than k plus 1, which implies pk plus 1 is true, because that is what I wanted to show. Therefore, if I have P1 is true, assumed for Pk, assumed Pk is true, and with that I showed that Pk plus 1 is true, that means Pn is true for all n in n. That means 2 to the power n is greater than n for any natural number n. Established. Next we have prove the rule of exponents ab whole to the power n is a to the power n into b to the power n by mathematical induction. So this is a general rule which we are all aware about. I just need to prove it with the help of mathematical induction. I will be taking statement Pn as ab whole to the power n is a to the power n into b to the power n. Again the same thing, prove it true for 1, assume it true for k, and with that assumption prove it true for k plus 1. That is it. That's the only drill you need to keep in mind. 3-step procedure. Apply in every question, get the result established. N equals 1. P1 is what? AB whole to the power 1. This is nothing but AB, which can be written as A to the power 1, B to the power 1. So for 1, for n equals 1, I have got AB whole to the power n is A to the power n into B to the power n. Therefore, P1 is true. Right? Assume Pn is true for n equals k. Let P, k be true for some k natural number, k is greater than or equal to 1, or strictly greater than 1 you can take, because for 1 we have already proved to be true. If Pk is true, that means AB whole to the power k is A to the power k, B to the power k. Because Pk is true means this is holding for n equals k. If this is holding, if this is true, I need to show Pk plus 1 is true. With this assumption holding, I need to show Pk plus 1 is true. That means I have to show AB to the power k plus 1 is equal to A to the power k plus 1 into B to the power k plus 1. That is what is the meaning of Pk plus 1 to be true. AB to the power k plus 1 should be equal to A to the power k plus 1 into B to the power k plus 1. Next, I have to show this when I am already given this. This step is given to me. For the same k, I have to prove AB to the power k plus 1 is A to the power k plus 1, B to the power k plus 1. Consider the left hand side, AB to the power k plus 1. This is what? If you consider this, you will be writing it as AB to the power k into AB to the power 1. But AB to the power k is already given to me as A to the power k into B to the power k. This is by mathematical hypothesis. And AB to the power 1 is A to the power 1 into B to the power 1. I know multiplication is commutative in real numbers. So I can just write this as A to the power k into A to the power 1 into B to the power k into B to the power 1. Right? Associativity holds with respect to multiplication. Commutativity holds with respect to multiplication in real numbers. What is this A to the power k into A to the power 1? It is A to the power k plus 1, and this is B to the power k plus 1. Hence you have established what you wanted to, which implies Pk plus 1 is true. If P1 is true, assumed pk true to prove pk plus 1 is true, and that is established. This implies by principle of mathematical induction, Pn is true for all n in n. It is true that ab whole to the power n is a to the power n into b to the power n whenever that n is a natural number. Next I have by induction again prove that 3 to the power n minus 1 is divisible by 2. Same thing, same very drill of applying the PMI, that is principle of mathematical induction, again and again. We need to show that this statement is true for all positive integers in place of n. Again Pn is that 3 to the power n minus 1 is divisible by 2. That means when you divide 3 to the power n minus 1 by 2, the remainder comes out to be 0. Same drill, n equals 1. P1, let's see whether P1 is true or not. Establish actually that P1 is true. P1 is 3 to the power 1 minus 1 is divisible by 2. That is 3 minus 1, that is 2, is divisible by 2. Clearly 2 is divisible by 2. What is the problem? So which is true? And therefore P1 is true. I have established P1 is true. Now I will assume Pk is true. Let Pk be true for any or for some k natural number where this k is greater than 1. Any arbitrary k I have taken, Pk is true. Pk is true means 3 to the power k minus 1 is divisible by 2. 3 to the power k minus 1 is divisible by 2. That means, see, when I am saying 3 to the power k minus 1 is divisible by 2, that means when you divide 3 to the power k minus 1 by 2, there is some quotient and the remainder is 0. Therefore, by division algorithm you can write dividend is equal to divisor into quotient plus remainder. So if 3 to the power k minus 1 is divisible by 2, this implies there exists lambda natural number such that 3 to the power k minus 1 can be written as 2 lambda. Because it is divisible by 2, that means this is the dividend, this is the quotient, dividend is equals to, this is the dividend, this is the divisor. So dividend is equals to divisor into some quotient plus 0 remainder. I am taking lambda as the quotient in the natural number set plus 0. 0 is the remainder, that has no relevance. Now if Pk is true, I need to show that Pk plus 1 is true. So I have to show Pk plus 1 is true. That means I have to show, what is Pk plus 1? 3 to the power k plus 1 minus 1 is divisible by 2. Now divisible by 2 means I should be, if I divide this by 2, I should be able to get some quotient and the remainder should be 0. Either you show this, or if 3 to the power k plus 1 minus 1 can be written as 2q. This means what? This is the dividend, 2 is the quotient, 2 is the divisor and q is the quotient. This is the dividend, 2 is the divisor, q is the quotient, remainder is 0. This itself would mean this would imply this and this would imply this. So we have to basically show that 3 to the power k plus 1 minus 1 can be written as 2q for some q natural number. Some q natural number, if it exists, for which 3 to the power k plus 1 minus 1 can be written as 2q. This would mean that when 3 to the power k plus 1 minus 1 is divided by 2, q is the quotient, 0 is the remainder, which would mean 3 to the power k plus 1 minus 1 is divisible by 2. So showing this is our target, to make some q exist such that 3 to the power k plus 1 minus 1 can be written as 2q, where q is some natural number. So I need to show that there exists some q natural number such that 3 to the power k plus 1 minus 1 can be written as 2q. Consider 3 to the power k plus 1 minus 1. I can write this as 3 to the power k into 3 minus 1, that is 3 to the power k into 3 minus 3 plus 2. I can write minus 1 as minus 3 plus 2. If you take out 3 common, you get 3 to the power k minus 1 and plus 2 aside. But 3 to the power k minus 1 is equal to 2 lambda by induction hypothesis. So this is 3 into 2 lambda plus 2. You can take out 2 common, you are left with 3 lambda plus 1. Lambda is a natural number, 3 lambda plus 1 is a natural number. I am taking, let this be equal to q natural number. So I have got, there exists a q natural number such that 3 to the power k plus 1 minus 1 can be written as 2q, which implies 3 to the power k plus 1 minus 1 is divisible by 2, and therefore pk plus 1 is true whenever pk is true. Whenever pk is true. By using pk is true, I have proved that pk plus 1 is true. And because k was any arbitrary natural number chosen, that means Pn is true for all n in n by principle of mathematical induction. Okay? Moving to the next question, we have prove this particular claim. Again, exact same thing. Again and again, the same PMI principle is going to be used in order to establish these results. So we have Pn this time is this, that's my Pn. Pn is 1 square plus 2 square plus and so on, n square is greater than n cube by 3. If I talk about for n equals 1, I actually get P1 as 1 square is greater than 1 cube by 3, which is clearly true. Just replace n by 1, what you get? 1 square is greater than 1 cube by 3, clearly it is true. Now I will be assuming for k, let pk be true. For some k natural number, k greater than 1. If pk is true, that means 1 square plus 2 square plus and so on k square is greater than k cube by 3. Sum of squares of first k natural numbers is greater than k cube by 3. I have to show pk plus 1 is true. That means I have to show sum of squares of first k plus 1 natural numbers, that means 1 square plus 2 square plus k square plus k plus 1 square is greater than k plus 1 cube by 3. That is what is my pk plus 1, 1 square plus 2 square and so on till k plus 1 whole square is greater than k plus 1 cube by 3. Before n square will be n minus 1 whole square, and so before k plus 1 whole square will be k square. How are you going to use this to prove this? Give it a thought and then we are going to be right back over the same question. Okay, so how are you going to use the very fact that pk is true in order to establish pk plus 1 is true? Let us assume the left hand side. Let us assume the left hand side. Consider 1 square plus 2 square plus and so on plus k square plus k plus 1 whole square. Now from 1 square till k square, actually I already have the value, it is strictly greater than k cube by 3 by the induction hypothesis. This portion is strictly greater than k cube by 3. K cube by 3 plus k plus 1 whole square. That's it. This portion is strictly greater than k cube by 3. So this portion plus this quantity is greater than k cube by 3 plus this quantity. So you get k cube plus k square. So this will be 3k square plus 1. So this will be plus 3 plus 6k whole upon 3. I want k plus 1 whole cube by 3. By 3 is already here. Somehow I want k plus 1 whole cube. What is k plus 1 whole cube? It is k cube plus 3k square plus 3k plus 1. So 3k square and k cube are already there. Plus 3k plus 1 I need. So I will be just writing this what I want. Plus 3k plus 1 I want. So I will be subtracting them as well. and rest of the quantities I would be writing. I am just trying to create k plus 1 whole cube. That gives me 1 by 3, k cube plus 3k square plus 3k plus 1 gives me k plus 1 whole cube, minus 3k plus 6k gives me 3k, 3 minus 1 gives me 2. Clearly k is a natural number, so this quantity is greater than 1, and therefore this complete quantity is greater than k plus 1 whole cube, and so this quantity is greater than k plus 1 whole cube by 3. This implies pk plus 1 is true when pk is true. Therefore, by PMI, Pn is true for all n in n. That's where you use your principle of mathematical induction to establish this fact. Okay, quickly note this down, then we are going to move ahead with the next two questions. Let's move ahead with the next question. We have, using again the principle of mathematical induction, prove that 41 to the power n minus 14 to the power n is multiple of 27. Okay, so basically 41 to the power n minus 14 to the power n is a multiple of 27. This is what is your primary statement. So Pn will be 41 to the power n minus 14 to the power n is a multiple of 27. Again, beginning with the same drill, n equals 1. P1 says 41 to the power 1 minus 14 to the power 1 is a multiple of 27. What is this? 27 is a multiple of 27. That is true because 27 into 1 is 27. So which is true? P1 has been established to be true. Now I will be assuming Pk is true. Let Pk be true for some natural number k where k is greater than 1, because for 1 I have already established it to be true. If Pk is true, that means 41 to the power k minus 14 to the power k is a multiple of 27. If it is a multiple of 27, that means by multiplying some natural number into 27, I will be able to obtain this quantity. This implies there exists some natural number lambda such that 27 into lambda gives me 41 to the power k minus 14 to the power k. I have just used the meaning of being multiple of, that means there exists some quantity with which if I multiply 27, I get this particular number. That means this number is a multiple of 27. This is something that I have with me. Let Pk be true, that means Pk is holding true. That means yes, there is existing some lambda for which 41 to the power k minus 14 to the power k can be written as 27 lambda. Using this, I need to show Pk plus 1 is true. That means I have to show what? Pk plus 1, that means 41 to the power k plus 1 minus 14 to the power k plus 1 is a multiple of 27. I have to show this. That means I have to show there exists some quantity with which if I multiply 27, I get 41 to the power k plus 1 minus 14 to the power k plus 1. If I am able to get such a quantity mu such that this holds, that would mean that 41 to the power k plus 1 minus 14 to the power k plus 1 is multiple of 27. Fine. So let us begin searching this mu. Consider this quantity 41 to the power k plus 1 minus 14 to the power k plus 1. You can write this as 41 to the power k into 41 to the power 1 minus 14 to the power k into 14 to the power 1. Now I will be adding and subtracting a quantity that is going to help me reach the very conclusion. 41 to the power k into 41 minus 41 into 14 to the power k plus 41 into 14 to the power k. I have added and subtracted the same quantity, written the left out expression 14 to the power k into 14. Now look at these two and look at these two. From here you can see 41 comes out common. Inside you're left with 41 to the power k minus 14 to the power k plus 14 to the power k comes out common. From here you're left with 41 minus 14. 41 to the power k minus 14 to the power k is already equal to 27 lambda. This is equal to 41 into 27 lambda plus 14 to the power k into 27. Clearly I can take out 27 common. I will be left with 41 lambda plus 14 to the power k. This is your natural number mu. You have been able to write 41 to the power k plus 1 minus 14 to the power k plus 1 as 27 into some natural number. This implies 41 to the power k plus 1 minus 14 to the power k plus 1 is a multiple of 27, which implies pk plus 1 is true, and therefore by PMI, that is principle of mathematical induction, Pn is true for all n in n. Understood? Moving towards the next question, we have prove by the principle of mathematical induction that for all natural numbers 3 to the power 2n when divided by 8 gives you the remainder always equal to 1. That is what I have to show. This is my complete statement. What is my complete statement in here? My basic statement Pn is what? That 3 to the power 2n when divided by 8 gives me the remainder always equal to 1. That's my Pn. So write down Pn, 3 to the power 2n when divided by 8 gives remainder 1. N equals 1, P1. 3 to the power 2 into 1, that is 3 to the power 2, which is 9. 9 when divided by 8 gives remainder 1. Is it true or not? When you divide 9 by 8, you actually get 1 as the remainder. That means either you say this or you say 9 can be written as 8 into something plus 1. This would mean that when 9 is divided by 8, whatever the quotient is, remainder is 1. And of course 9 can be written as 8 into 1 plus 1, and that means when 9 is divided by 8, the remainder comes out to be 1. 9 when divided by 8 leaves the remainder 1, which is true, as 9 can be written as 8 into 1 plus 1. That means when 9 is divided by 8, quotient is 1, remainder is 1. Therefore, P1 is true. Let Pk be true. Let Pk be true for some natural number k where k is greater than 1, because for 1 we have already proved. If Pk is true, that means 3 to the power 2k when divided by 8 gives remainder 1. This means when 3 to the power 2k is divided by 8, there is some quotient and remainder is 1. That means dividend can be written as divisor into quotient plus remainder. This implies there exists q belonging in n, that is the quotient, such that 3 to the power 2k can be written as divisor into quotient plus remainder, where the remainder is 1. 3 to the power 2k can be written as 8q plus 1 for some natural number q. That means 3 to the power 2k when divided by 8 gives quotient q and remainder 1. So either you write in form of statement that 3 to the power 2k when divided by 8 gives remainder 1, or you say there exists a natural number q which is acting as the quotient when 3 to the power 2k is being divided by 8, such that the remainder is coming out to be 1, and therefore 3 to the power 2k can be written as 8q plus 1. Using this, Using this, I have to show pk plus 1 is true. I have to show pk plus 1 is true. That means I have to show when 3 to the power 2 into k plus 1, when this is divided by 8, gives remainder 1. That means I have to show there exists some r natural number which is acting as the quotient when 3 to the power 2 times k plus 1 is divided by 8, such that when 3 to the power 2 times k plus 1 is divided by 8, I am getting r as the quotient and 1 as the remainder, so that dividend can be written as divisor into quotient plus remainder. If I am able to establish this statement, this would mean that this is holding and hence pk plus 1 will come out to be true. It is a backwards thing that we are going to show. So consider this 3 2 to the power k plus 1, which is 3 2k plus 2, which is 3 2k into 3 square, 3 to the power 2k into 9, but 3 to the power 2k is given as 8q plus 1. So this is 8q plus 1 into 9, it is 72q plus 9. This can be written as 8 into 9q, right, plus 8 plus 1. 8 into 9q is 72. 9 can be written as 8 plus 1. I can take out 8 common, I have 9q plus 1. Plus 1, and this is what is your r. I have got a natural number r such that 3 to the power twice of k plus 1 can be written as 8 into r plus 1. That means when 3 to the power twice of k plus 1 will be divided by 8, this r will be the quotient and 1 will be the remainder. This implies 3 to the power twice of k plus 1 when divided by 8 gives remainder 1, which implies pk plus 1 is true. That is what is pk plus 1? Assuming that pk is true. We assumed pk is true, and that is what we used in order to replace 3 to the power 2k by 8q plus 1, because that was what was already holding, right? pk plus 1 is true when pk is true. Therefore, by principle of mathematical induction, Pn is true for all Nn. Hence, we have proved, and that completes my discussion over all the questions. That's it from my side. Thank you.